Hello, my name is Sono Kim. I was a Google Summer Code contributor this summer working on new JIT infrastructure in LLVM. The major part of my work is writing new backends for a JIT component called JITLink. In particular, I wrote a Alpha AX64 backend and Windows COF backend for JITLink. The Windows COF JITLink massively enhanced the Windows COF support in the LLVM JIT APIs. So today I want to work through a demo Windows JIT application to demonstrate how to use these new features and demonstrate the power of this JITlink, which is like not really well known to the public, but very powerful because it has access to very low level components. So here's outline of this talk. We're going to talk about how does JIT work inside LLVM. And we're going to talk about some motivation for JITlink. And we will go dive right into some examples, building some Windows JIT application. And we're going to write some plugin too. And I'm going to share some tips on using JITlink in COF and tips on developing JITlink itself. And finally, I show Clang level demo, putting all these things together. So JIT inside LLVM works a bit differently from typical JIT compiler in other languages. So if you look at this typical executable generation pipeline in LLVM, we have a front end which can be Clang, and we have a back end which can be inside LLVM core. And LLVM MC emits object files to the file system. And we have a linker such as LLD that links object files in the file system to one executable file. The JIT inside LLVM works by tweaking this last linking step. So here is a JIT execution pipeline in LLVM. We have object file instead of dumped into the file system. It's still in the memory. And we have JITlinker, which links the object file inside the memory into executable form, but still inside the memory. So benefit of this approach is that it shares a huge portion of pipeline with AOT words. So if we just turn on all the optimization, then there's barely no performance difference between them. And the major benefit, which is the most important one, is there's fewer breakage caused by LLVM internal code changes, because JIT component of LLVM is not well as maintained as like the other mainline features. This is really important for us because object file format is relatively standardized, so there is fewer breakage caused by fastly moving LLVM core. The thing is, we already had JITlinker implemented called runtime DYLD. The problem is it has various caveats, and one of these caveats is small code model was unsupported. This is one of the major caveats of runtime DYLD because usually small code model is a native code model in major terms. So for AX64 had a serious code against large code model that caused random hangs and crashes in Julia. Can you hear me?
Yes.
Okay. And static initializer or TLS were supported but very limited way. Especially TLS was essentially not supported because there are some code for it, but yeah, it's not working. And in general, runtime DYLD was developed in a bit of ad hoc fashion. And what I mean by it is error handling or code design was not consistent across different architecture and platforms. And in terms of this talk, COP support existed, but very unstable. Some people even used Alpha on Windows and with various patches on LLVM because COP support was so unstable. So we have a new JITlinker called JITlink that are designed to mitigate this issue. Now small code model is supported with new memory allocator. Runtime features are fully supported, including static initializer and TLS. And there's this nice generic linker object abstraction called link graph, which greatly simplifies the development of complicated linking rules, while achieving like great deal of code sharing and infrastructure sharing. And this is actually the main reason why it is easier to fully implement native object file features inside JITlink. So how good is COP supporting JITlink now? It is capable of linking object file directly generated by MSPC. The reason why we are now able to link native object file directly is we have COMDES with external linker directive, DLL import stop, or CRT initializer. These kind of native object file features got implemented properly. And it is able to JITlink the entire VC runtime. So you can just load up a mfvcrt.lib into J session, and things just work out of self. And linking to Microsoft SQL library work out of self too. And things are incremental by default because org is designed that way. So I'm going to jump right into some examples right away. We're going to build a mini LLI tool from scratch. LLI is a LLVM command line tool that executes the LLVM IRIS written inside .edit file. And .edit file can be generated from any frontend such as Clang. So what we're going to do is start by implementing mini LLI and advanced JIT on top of it. So here's the code for template code for initializing LLVM at work, and it has some code for enabling JITlink. Something important we need to do now is we need to load about org runtime. Org runtime is a collection of runtime code that is used to implement complicated runtime and G features. Loader runtime function can be used to load org runtime into J session, but we do need to grab an org runtime file from compiler or build. So I grab one over here. This is the org runtime file. So what we're going to do is we're going to just copy paste the name of this library. And load org runtime like this. We actually have a patch that adds this functionality to Clang, but it's not merged yet. But I think it's going to be merged soon. So if we compile this thing, we see this hello world program is running. This hello world program is from this main.edit file. This main.edit file was generated from this main.cpp file using Clang. You can use this command to emit main.edit file from main.cpp. So what we're going to do is we are going to tweak this main.cpp little by little and use Clang to emit main.edit file and run this main.edit file using the program we're just building. So one other thing I want to try is, since org runtime is loaded up and JITlink is enabled, pretty much majority of the features just work out of self. Sine and cosine function from VC runtime library just work. And S3 map, S3 mutex, or S3 count, this STL functions work too. So I can actually show it right here. I'm going to copy paste this file. So this is like a basic code that has a STD map int, and it says M of 1 to the 53, and it prints the value of the M of 1. I use Clang to emit main.edit file and run that main.edit file from here. You can see that it just learns perfectly. Another thing, one thing that's cool about this is we have SCH and C++ extension support. So let me show you right here. This is C++ extension code demo. Copy paste it over here. We have a function that is drawing on the exception, and we have a try and catch that draws that catches that exception. So if you use clang to implement the editor file around the program, you can see that exception is successfully caught. And SCH exception works too. Here's the code that demonstrates SCH exception. So the thing about this code is that this reciprocal function receives one argument and divides one by that value. But since we're giving it a 0, it will cause a division by 0 error. So normally this would have crashed. Like this, it is crashing. But since we have a SCH exception handler, oh, I forgot to clean. It is not crashing, just printing d by 0, which is executed here. We put 1 over here. Now it doesn't crash, printing nothing. One other thing I want to try is I want to load up a static library built with MSVC into GSession. So this is the static library we have right here. And what we're going to do is we're going to load up this library into GSession. We can do that by using the code, something like this. So I'm going to use this code over here. Place it right here. And since we have a static library loaded onto GSite, we can use this function declaration in main CPP here. I'm going to remove this new stock. And we can just call this function. It works perfectly. Notice that object file generated by native compiler got successfully linked by JITlink. Since static library is a collection of object files, the object file is from MSVC, but they were got linked like without no trouble. And native static initializer inside a static library worked out of self too. If you look at the source code of the static library, this function is doing it is printing the value inside the font, but this font is initialized by using this function, which is just returning cosine of 0, and cosine of 0 is 1. So since these static initializers are ran, we're seeing 1 over here. So that is quite basic usage of JITlink. And I want to do something more complicated that is fully using the power of JITlink. So before going into that, I want to talk about some overview of JITlink. So we have different object files, and we have different architectures for binary code. And since we have a different formats of object files and different architecture of binary code, we want to support a combination of this. And in order to do it while achieving a great deal of code sharing, JITlink converts object file into generic linker object representation link graph. And then it performs generic memory allocation, symbol resolution as described inside edit link graph, and performs architecture specific allocations. So everything is centered around this data structure called link graph. Here's what's actually inside link graph. We have block, which is chunk of bytes. It can be either code or data. We have a symbol that is exporting this block as some kind of name. And we have an ask that essentially asks JITlink to patch certain portion of the instruction to point at this symbol. This is equivalent to what they call relocation in standard traditional object file. So the objective one is going to be, we're going to write a JITlink plugin that print the summary of onion frame of each function contained inside the .p data section. So here's how onion frame looks like on the windows. We have a .p data section, and it contains array of runtime function structures. And each runtime function structure has a code range of the functions and the onion information. For instance, it has information how to onion the stack of a function, or whether it has an exception handler. And the address to the exception handler that can be inside the code. And these runtime functions get us emitted to .p data section of object file. And JITlink plugin system allows us to this .p data section. Here's basic example of JITlink plugin. We can ignore this part. We can only focus on this part. So this is a callback, C++ lambda over here. This callback gets called in specific linking phases. And inside this callback, you can view what's inside this link graph over here, and even modify link graph as much as you want. And this prep run is specifying the linking phase. We have total of 5 of linking phases where we can insert custom passes. And this prep run is the first linking stage. So let me actually try coding up some plugin right away. So here's a template code for the plugin. I'm going to use this code right here for client. And if you just run this right away, it is printing something like infinitely. This is because we're loading up Oracle runtime, and it is collection of object files. So we're loading on like massive number of object files. So it is logging everything. So I'm going to comment this out. So since we have a preference linking phase where it dumps what's inside link graph, it's just logging everything. So since I have commented out this load Oracle runtime, now it only shows one link graph, which is inside the object file of the main.ll. And here you can see we have a block which contains the chunk of ice. But look at here, this is main. So what this is doing is this block gets exported as main because of this symbol over here. So this block must have contained the binary code of the main. And we see the edges over here patching some instruction to target print function, which totally makes sense because we're calling print like this. We also see a mangled name of f over here because we're calling f like this. And if you scroll down a bit bottom left right here, then we see the .p data section, which contains the unwind frame of the each function. And we see the section can consist of multiple blocks. So what we're going to do is we're going to poke into this .p data section, but by using JITlink plugin system. First, I'm going to uncomment this line and add some of it a hack. So I'm going to create a Boolean variable called log. And I'm going to set log to true after Oracle runtime is loaded up. And if log is first, I'm going to just skip everything. And instead of dumping what's inside link graph, I'm going to poke what's inside the .p data section. But here I'm going to use, instead of preference stage, I'm going to use postfix stage. The reason for why using post-fixed stage is because it's the final stage of the linking pipeline. So all the addresses are assigned and memories are allocated. So it makes sense to look at that part. So inside here, we can now look at the section of .p data. And if section exists, we go over one of each block, iterating through this one block by block. So we're going to iterate over blocks. And since each block contains the array of runtime functions, we're going to convert this into the runtime function pointer. And we have to know the size of this array, which we can know while dividing the size of the block by the size of runtime. Now, finally, we can iterate through every of this. And we finally get one nice runtime function. This runtime function entry has begin address of the function, which we can get like this. And also end address of the function. And this gets generated for pretty much every function inside the object file. So now we are going to just print this. And just run it. And we can see these addresses are printing right now. And these address numbers are quite random. Like we are not really sure like this is from where. So what we want to do is print the function name for each function entry so that we can be sure this is indeed come from this main.cpp file. In order to do that, we are going to modify this path over here. So what this is doing is iterating over every symbol that this graph is defining. And we can know the address of the symbol like this and get the name of the symbol like this. Since we know the address and name of every symbol, what we can do is we can create a map from address of the symbol to the symbol name. And we can fill this map inside here. And since we have this address to symbol name map filled it up inside this path, now we can use this inside here. And here, all we can do, we can print the function name by using this table. I'm going to run it. And now we can see the function name like this. We have a main function and we have a print function. This is actually a weak symbol of the print, deeper information. So we are not sure that this actually came from this main.l object file. And this runtime function tree, of course, doesn't only contain the beginning and end of the function. It also contains various useful information such as whether the function has exception handler or not. We can know this by looking at the unint info structure inside the function. We get unint info. We have image based and function. We can look at the flags of this unint info. And now we can know if this flag has an E handler, then this function must contain handler. Otherwise, this function doesn't contain the exception handler. And right here. And we see that every function has no exception handler right now. And this is because, like, if you look at the code right over here, then it doesn't really have try and catch or like SH exception going on. So we're going to copy paste this example provided right here. And this code has a try catch statement inside the main. So if we use clang to animate the data file and run this again, we now see that main function has an exception handler. For your information, SCH exception handler works in the same way. So if you have a try except statement inside main function, then it will have exception handler too. So what works under the hood is Windows API, Windows OS is trying to unint the stack one by one. And if the function has an exception handler, then it will execute the handler. And finally, I want to show you something cool. There's something called unint operations. I created this print unint operation function beforehand. There's nothing cool about it. It has one big switch statement that prints the values. But if you run this thing, we can see this kind of stack operation right here. So this print function is allocating smart size area on the stack, which is 56 bytes, and it is pushing 2 registers. So what I can do to unint the stack of this print function is you can pop 2 registers. After that, you can deallocate area on the stack with this specific size. And there also one of the basic example of building JITlink plugin, and I want to do something even more fancy. So objective 2 is show disassembly of function that just raise exception. How we're going to do is let's say this func raised the C++ exception, then it will internally call CXS draw exception function. Since JITlink has every information related to linking these functions and symbols, we can swap this CXS draw exception function to trampoline. We're going to generate this trampoline inside JITlink, and the trampoline structure will be something like this. It will first save some registers and call draw intercept function, and after that it will call CXS draw exception function, so that it can go on usual exception handling routine. This draw intercept function will be the C++ code that prints this assembly of the function, this func function. So this is the most exciting function. So this is the code that generates the trampoline inside JITlink. So first we have a write save read code, which writes a saving register code in x86 to code buffer. And code buffer is nothing cool. It's just std vector character. And we are going to write one call instruction to the code buffer. So after that, the code buffer will look like this. You can ignore this, the first part, it's just register saving code. The last part is important. It is a call instruction to draw intercept function, but this green box is 0 right now. And this 0 is displacement to the function we want to jump to. But this is 0, it will just go on to the next position doing essentially nothing. What we want to do is fill this 0 to the actual display, this point to the draw instruction. But the problem is we don't know the address of this part right here, right? Yeah, because this code buffer is just temporary buffer, and we don't know when this buffer, where this buffer would end up after all code allocation things are done. And we don't even know the address of the draw intercept symbol too, so we can't even calculate the displacement. So what we can do is we can add JITlink edge to this. So this is the code that as an external symbol to draw intercept and use that symbol as target symbol of JITlink edge. So what this JITlink edge will do, it is going to patch this portion of the bytes to the actual displacement from the final point of this instruction to the draw intercept symbol. So here is a finalized create trampoline code. So this is the code we looked at before, and there's some other boilerplate code. And this draw intercept function will be ran if you draw something inside C++ side. So what we have to do is we have the code for creating trampoline, but we haven't swapped the symbols yet. So I'm going to swap it by using the pass over here. And we are going to iterate to every blocks inside this graph. And I'm going to iterate to every at or location inside this blocks. And if the target symbol is CXS draw exception symbol, then what we can do is inside this we can swap the symbol into trampoline. So we have symbol trampoline, and if there's no trampoline, then we create a trampoline. And we swap the target symbol to that trampoline. If this is done, if you draw something from C++ side, then it'll call this function first. So we can print some random value here. Hello, compiler search group, and run this. And if you look at the code of the main.cpp, it draws some exception, and after it draws an exception, it is a catch statement that catches the exception. But since we have intercepted this draw call, we see this draw intercepted. Hello compiler research group, and call draw exception, which is the exception handler over here. So we essentially kind of implemented something hooking, but only using the JITlink. And this is very powerful because you can call basically any symbol you want, and it will handle all the low level details of managing the displacement and stuff. Now what we want to do is inside this draw intercept function, we want to show the disassembly of the function that just raised the exception, which is this draw exception function. This PC is the call to the draw exception function. So what we can do is find the function entry that contains this PC and find the beginning and end of the function and disassemble that area. We can do it by creating a table over here. So since we have a beginning and end of every function and the start address, we can create a map of function entry. And save it over here. And after that, we can use this map like this. So we are going to use upper bound to find the function entry that is one past the what we want, and we get the one that is previous to. And we get the function entry. And since this only guarantees that beginning of the function is less than this PC, we do need to check it doesn't go past it. So here we know the beginning and end of the function that contains this, that contains the call to this draw. And if PC is over the end, then we return it, since that means this function doesn't contain this PC. And since we know the beginning and end of the function, now we can just print the name of the function. Is exception. Bowline. And we can now disassemble this whole byte. All right. Now we see this draw exception function and the disassembly of the function. So if we, for instance, call the print like this and run it again, now we see the call to print is generated because this is the real disassembly of this draw exception function. So there was a plugin example that fully uses the power of JITlink, and I hope it shows some glimpse on what JITlink is and it's how to use it for building really complicated JIT features. It is essentially giving you control over like very low level details of linkers, so you can do so many things with this. Finally, I want to talk about some tips on using JITlink inside the COF. There's some various details to it. So when org runtime is loaded up, it actually loads up PC runtime library files such as mnspacert.lib. And we do this because these files are required to load up org runtime because we have to JITlink the org runtime files too. So carriers need to make sure org and PC runtime library files are available. By the PC runtime library files are automatically detected from VC toolchain directories, but this can fail if user doesn't have a VC toolchain installed. You can customize the behavior by using this class called call VC runtime bootstrapper, or use in-process specific runtime symbols like before, but you do need to export symbols manually, like we used to do in the runtime device. Another thing to care about is small code model. So when small code model is enabled, compiler assumes that all symbols within the same executable are located close together. So we have to make sure that the displacement of the instruction doesn't go exceed 2 GB, but we cannot pass the instruction on demand because COF x86 relocation point to the middle of the instruction bytes. But x86 instruction encoding is not possible to be read backwards, really. So especially because of the rocks prefix. So we can't know the start of the instruction, so we cannot really do the fancy patchings. So you really have to put everything into the one JITlink. If it's inside one JITlink, then JITlink memory allocator will enforce the distance from the first symbol to other symbols to not exceed larger amounts, so everything will just work fine. But if you want cross JITlink call, then you have to, for calling function, you can just call it in usual way, either internally generate or jump stop, which will handle everything. But for accessing data symbol, such as like variable inside other shared library function, then you have to use something called import stop. You can do this by adding DLL import attribute to the function. I mean the variable, or put imp prefix on the symbol name. So finally, I want to show the Clang Apple demo. So it's using everything combined. The work hasn't been upstreamed yet, but like the patches are there. I need to just polish them. But it's using the like new features that we discussed before. So we can have a print function calling, and we see hello world is working. And we can access to, I have to include the string. Map of int of string. And we set this to high. And we print value. So you see STL functions get linked CS tier. So you see STL functions get linked very out of cell. It just works. And something that we didn't have before, the exception handling works too. So if you have a draw exception, and this function we just draw compiler research, and I'm just gonna name it too because we don't want to crash the program. I think it doesn't matter though. So, and this function will handle exception, and it will have a try, which have draw exception, and catch. It catches the exception, and just print the what's inside of what's inside the exception. It will return 0, and we run this handle exception. Then you see the exception get caught very nicely. We can even use SCH exception here, Windows H. And for here, we are going to use a reciprocal, and this will be the division by 0. And we're going to, if you call let's proof of 0, then it is just crash entire program. But we're going to do the SCH except, and here we're going to have a try reciprocal of 0 and accept exception execute handler. And inside this, we'll write some call. And return 0. And call this function. You see division bar is still is caught. And if we just call this reciprocal 0, then it just crashes. This can be used to actually catch null pointer dereference to and pretty much every hardware exception. So this is totally new capability of Clang Apple. Yeah, that was it for me. Thank you very much. Do you have questions?
Thank you, Sonho. It was really exciting to see how many things you can do now with Org v2 and Windows. Questions or comments? Okay, I have one on my own. So you showed a bunch of examples, but how many of those examples are available for people to basically replay? Are they available somewhere on GitHub?
Oh
Or...
yeah, I just have the code inside the GitHub, but I haven't published that yet. But I will do it shortly.
Okay.
And maybe also one question, if I may.
Yeah, go ahead.
A lot of these things that you can do are pretty standard. I'm wondering whether there is a list of plugins available to do these types rather than having to re-implement it yourself.
Oh yeah, so I just wanted to show that it has access to very low level, like the linker object details.
Mhm.
So you can like pretty much access like the symbols of the object file that is just getting linked, and you can replace the symbols, and you can replace the add more the locations and even more code. So I just wanted to show you the capability of this JITlink. And the main like functionality provided by JITlink is probably this part. So these are the features that are essentially provided by JITlink for the like user perspective, because
Right.
this advanced C++ stuff didn't work out of cell before without JITlink. It kind of worked with some patches, but like it requires some more care. And SCH and C++ exception support, this is something we never had before without JITlink.
I think the question was also in the with respect to, since these are kind of standard operations now and maybe interesting for many people, are these plugins available, or what would be the way to deliver these plugins to like mere mortals and to just use them without having to implement them?
Just to give an example, what is very common in HPC is, in order to understand what a program does, you want to shim functions. Right now, it's a bit of a mess because you use the shared linker, and then many programs, especially Fortran programs, they prefer to use static object files. So it will be awesome if you could just load one and then patch up the file after the fact. And that should be a simple operation where you just provide these are my input symbols and these are the symbols that I want to have instead, and just be done with it. So something, that type of functionality that would just be available where you do not need to understand the internals, but just, the symbol becomes that one and then off to the races.
Yeah, that's a cool idea to do.
Lang replied in the chat that we do hope to build up a library of common plugins in LLVM. So eventually,
Yeah, that would be awesome.
eventually that would show up in there, I guess. But I mean, yeah, we can make a request for comment if we have like compelling examples, and then we start building that up.
The one I just mentioned, it's in HPC, they're gonna love it.
Yeah, okay, I need
Do
to
it all the time.
I need to.
Oh, can you actually send like some spelling and like the text, some kind of like link to it? Because like I might actually look into it.
I'm not really sure link to it, but I can show you a code example of all the mess that we do. Can probably find some older codes of all kinds of different tricky flavor. People do all kinds of things in order to replace systems symbols. Because often libraries are some libraries now these days have proper support, like MPI, for example. You can get hooks for every call so that you can intercept the messages and all this kind of stuff. But often libraries are proprietary, and then the only thing you can do is to shim things. And so you mess with the linker statically, and then you rebuild your whole program, and it's just annoying. But I'll send you a sample of the last one. I think that's a good one as an example, because that's exactly static libraries, and then the how you redefine the linker symbols to go from one to the other.
Cool.
Okay, so looks like we will have some follow-up on this. More questions or comments? Okay, if not, then we're a bit past the hour. Thanks again to Sunho about